Welcome everyone. It is chapter 21 of the Crystal Clear Electronics video series. We present a chapter of the curriculum called Immediate Events in the Software Interrupts, written by Péter Farkas and Csaba Apró in two separate videos. Today's lead presenter, Ádám Szabó, is a mechatronics engineer who has been involved in writing and proofreading the Crystal Clear Electronics curriculum.
Thank you very much for the introduction to my fellow presenter, Szabolcs Veréb. You already met him earlier in the 17th chapter of the curriculum. Szabolcs is an electrical engineer and he's finishing his PhD at the university. It's also important to mention that Szabolcs was the author and proofreader of some of the chapters of the curriculum. You may have encountered interrupts from a very young age. An interrupt means that we pause or stop what we are doing to perform another, more important task that requires immediate action.
Like when I was a kid watching TV and my parents asked me to take out the rubbish. I stopped watching TV, got up, took out the rubbish and sat back in front of the TV.
Similarly, an interruption is when your cat is about to knock the mug off the table while you're reading a book. You quickly stop reading, jump up, grab the mug or the cat, clean up if necessary, and then sit back to read.
Let's take a look at what interrupts mean in the world of electronics. Let's get started with the lesson.
The electronic devices and systems that surround us usually don't work on their own, but they respond to events in the outside world. The systems and their inputs can be relatively simple, such as a remote and its buttons, or complicated, such as the autopilot of an aircraft. Even though an aircraft autopilot sounds very exciting, we will stick to a simpler example to understand one of the key systems inside the microcontroller and how to use it. In this chapter, we will write a program which can count between 0 and 7 and increase or decrease the counter by 1 on the press of a button. The current counter value is displayed in binary with 3 LEDs. On the demo circuit, 2 buttons are connected to 2 pins of the Atmega16A microcontroller, one to PD2 and one to PD3. These buttons will act as the up and down counter input buttons respectively. The 3 LEDs are connected to PA0, PA1 and PA2. You can see the schematic in the figure. You can also see it here in the schematic. The push buttons are connected to the inputs of the microcontroller with pull-up resistors.
Our first task is to read the status of the push buttons. You've seen solutions to this in previous videos, but we'll go through them in detail.
One solution is to enter an infinite loop in the main part of our program and read the input, which has a button connected to it continuously. If the input is logic 1, we know someone pressed the button and we can increase or decrease the counter. In our example, there is a small difference since the button input has a logic high value when the button is not pressed. When the button is pressed, the input is connected to ground via the button. This is called an active low connection. It also means that the button press can be detected in the software with reading of 0 from given bits of pinned. We configure the ports as input and output the same way we have learned before and write the program.
In the program code, we want to check the logical state of the D port pins 2 and 3. To do this, we need bits with local values 2 and 3 of the PIND register, which can be obtained by bit masking. Place value is 2 squared, that is 4, and place value is 3 is tripled, that is 8. Therefore, the correct value can be obtained by performing a bitwise AND operation on the PIND register or the number corresponding to the local value. The exclamation mark negates the logic value. We need this because our button's hookup 0 is active, meaning that when the button is pressed, the microcontroller's pin is at a low logic level.
So, in the main function, after calling the IOInit function that sets the direction and value of the microcontroller's pins, we increment or decrement the counter in the infinite loop whenever a button is pressed, taking into account the maximum and minimum values that the counter can take. As Szabolcs has mentioned, the exclamation mark in the if conditions is the logical negation operator, so the value of exclamation mark pinned and 0x04 is true if the PD2 pin has a logical low value, which is exactly when the button is pressed. And at the end of that loop, the counter value is displayed on the LEDs. Szabolcs, please upload the code to the microcontroller and let's see what happens.
Alright, just a moment. Loading the code. Bits are flying. Everything's fine. Let's see, let's just hit the count up. Oops, all 3 LEDs lit up immediately. If I count down, they all turn off. That's not exactly what I expected.
That's not exactly what we intended, so what causes this weird behavior? Think about how long an average button press is. No matter how fast you are, you'll surely keep the button pressed for a few hundred or 10 milliseconds. Szabolcs, what is the clock speed of the microcontroller?
I think 8 MHz. Completing one iteration on the infinite loop takes a lot more than one clock cycle, but it's still only takes a few milliseconds or even less. So while our super quick button press seems very fast to us, the microcontroller has time to examine the input a few hundred times while the button is pressed. As the input is always 0 during that time, it increases or decreases the counter value until it reaches the limit either 0 or 7. This all happens so fast that the individual counting of the LEDs cannot be perceived by our eyes. We only see the end result of no LEDs or all LEDs lighting up.
And how can we solve this problem? We could try and save the current state of the button, which can be 0 or 1, and only increase or decrease the counter if the previous button state was 0 and it has changed to 1. This means we wouldn't wait for the button state, but for the moment the button is released. There is a major issue with this solution as well. In a real-world application, the microcontroller has many tasks that it needs to do in every iteration, and that usually takes time. We're not going to perform such complex operations, but somehow it would be nice to see what effect this would have on our code. Add a for loop inside our main loop that does nothing useful, but count to 500,000. It could seem that this has no purpose, but we only need something that runs for a while, and that's enough to demonstrate the task. Szabolcs, what can we see now after modifying and uploading the program?
Well, you need to upload the code first. Okay, we've already done that. Let's see. So I pressed the button and it only turned on after a while. While pressing, it doesn't notice every button press, but it counts well. If it detects the button, it works perfectly fine. Again, not exactly what we wanted, but something. It's better than it was.
Think about why this happens. For the better part of the main loop, our microcontroller is busy with counting, so it can only look at the buttons for a short amount of time before going back to counting again. That is, our program spends little time in if conditions. So, if we don't hold the button down long enough, our program will just miss the event. So this operation can't be called reliable in any way. There should be a way of detecting only the rising edge in the signal, but it can be implemented at any time, wherever the implementation is in our program. Luckily, others have bumped into the same problem before and come up with a solution called interrupt, which is a pretty catchy name.
The interrupt can be generated by an external or internal event that requires more important or urgent execution than the currently running code. During an interruption, the current program is interrupted, its state is saved, the event is handled, and then the state of the original program is restored and the program continues to run.
We can use dedicated inputs of the microcontroller, where if a pulse or a logic level change occurs, the microcontroller interrupts whatever it was doing and executes a special function we can specify the contents of. In the function, we can react to the event, and after that, the microcontroller continues execution from where it left off. This function is called external interrupt, indicating that the microcontroller enters an interrupted state because of an external event of one of its digital inputs. We call this function interrupt handler. Now we can see that this will provide a solution for the above mentioned problems. However, more questions might arise. What other types of interrupts exist? How does the microcontroller recognize the change of the input while it is running the main loop? What happens when new, one or more interrupt events occur while the interrupt routine is still running? Will we be able to notice these? Will this end the running interrupt routine?
You will find the answers to these questions in the upcoming video. Now, this brings us to the end of the first video of chapter 21. Thank you very much for joining us. See you in the upcoming video.
Bye bye.
Bye.